gross iron area, Ks into AGI, taking stacking factor, Ks is equal to 0.9 into 0.5 d square. AI is equal to 0.45 d square. We consider some ratio. First, ratio of net iron area and area of circumscribing circle. Net iron area upon area of circumscribing circle, that is 0.45 d square by pi by 4 d square is equal to 0.58. In other words, only 58% area is utilized by the iron. Ratio of gross core area and area of circumscribing circle. Gross core area upon area of circumscribing circle is equal to 0.5 d square by pi by 4 d square is equal to 0.64. In other words, 64% of area is covered by gross iron. So for cruciform two-step core, in this case, we need to find out dimensions A and B such that it gives maximum area for given circumscribing circle diameter D. So we can write gross core area AGI is equal to AB plus AB minus B square. As B square is common area of two rectangular sizes of A into B. So AGI is equal to 2AB minus B square. Also we can write A is equal to D into cos theta and B is equal to D sin theta. So AGI is equal to D square sin theta cos theta minus D square sin square theta. D square sin 2 theta minus sin square theta. Now for this area to be maximum, we can write d AGI upon d into theta is equal to 0. From this we get theta is equal to A is 31 degree. A is equal to d cos 31, 45 is equal to 0.85 d. B is equal to d sin 31, 45 is equal to 0.53 d. Putting this AGI expression, AGI is equal to 2 into 0.85 d into 0.53 d, and in bracket 0.53 d square. So we get AGI value is equal to 0.618 d square. Net core area AI is equal to 0.9 AGI is equal to 0.9 into 0.618 d square. So net core iron area is equal to 0.56 d square. So ratio of net iron area and area of circumscribing circle. Net iron area upon area of circumscribing circle. So we get other words, we get 71% area is utilized by the iron. So for two step, we cover 79% of area by gross iron. This is seen that as we increase the number of steps, the area of circumscribing circle is more effectively utilized. Following table gives the result of various steps. Here is results. For 2 step, for square step, net iron area of circumscribing circle is 58. Gross area is 64%. For cruciform 79%. Gross core area utilized by iron, and 71% net iron area. In 3 step, 84% gross core area utilized by iron, and net core area is utilized is 75%. In 4 step, 87% gross and 78% net. So relation between flux density and current density. Before we discuss choice of flux density, let us see how core area is calculated. Voltage per turn is given by E is equal to K into under root of Q, where Q is equal to kVA rating of transformer and K is constant, which is chosen from table. Thus, value of ET is found out. EMF equation is given by ET is equal to 4.44 F PHIM. From this, flux is calculated as PHIM is equal to ET by 4.44 F. After this, area of core can be found out by assuming suitable value of maximum flux density BM, net core area AI is equal to PHIM by BM, gross core area AI is equal to AI by KS, where KS is equal to stacking factor. Now we discuss selection of flux density. From the above discussion, it is seen that valve of maximum flux density controls the core area. Thus, if we select higher value of flux density and net core area is reduced, so there is reduction of iron weight and hence cost of iron. This also reduces diameter of circumscribing circle, which reduces length of mean turn. This reduces I square R losses, as well as there is saving in cost of copper. However, iron losses are increased due to higher value of flux density. In addition to its temperature, it is increased, which requires more cooling arrangement. Higher value of flux density saturates. Higher value of flux density saturates core and increases magnetizing current, also result in the production of undesirable harmonics.